So the next talk is given by Etienne Bellin about independent number of large random trees.
That's it. Thank you for the introduction. So first of all, I would like to thank the organizers for tonight's conference. I'm quite glad to be here in person because this is my first time coming to the US, so I'm quite happy to be here. So indeed, I will talk about independence number of large random trees. Okay, so okay, sorry. Okay, so let me first define the object of interest, which is the independence number. So first of all, if we have a general finite graph G, okay, we say that a set of vertices is an independent set if no pair of vertices is linked with an edge. Okay, and moreover, we say that an independent set is maximal if it is maximal in the sense of the cardinality. So notice that here we are not talking about the maximality in the sense of set inclusion, which would also be interesting, but here we talk about maximality in the sense of cardinality. Okay, in an example, here we have a graph with 9 vertices, okay, labeled from 1 to 9. Okay, and if we look, for instance, at the set of vertices labeled 2, 4, and 5, I have an independent set because 2 and 4 are not linked, okay? Even though there is a path of edges, it's not linked with the path of length 1, okay? 4 and 5 are not linked, 2 and 5 are not linked either, so this is an independent set. But it is not maximal because, for instance, if I add the vertex 7, I have a bigger independent set. And indeed, in this particular example, we can easily see that 4 is the maximal cardinal you can have for an independent set. Okay, so 2, 4, 5, 7 is maximal. Okay, we also have, for instance, in this case, 3, 4, 6, 9, which is also a maximal independent set, cardinal 4. Okay, just a quick remark. The maximal independent set has no reason to be unique, as we saw in the last example. Okay, and as you can guess, the independent number is just the size of a maximal independent set. Okay, and I call it alpha of G for a graph G. Okay, and our goal is to study this number for large random trees. Okay, and more precisely, I will look at Tn, and Tn is a random Bellin-Galton-Watson tree. Okay, so BGW means Bellin-Galton-Watson. Okay, also known as Galton-Watson trees, and condition on having n vertices. Right. Okay, to do so, I will introduce a notion of tricoloration of a tree. Okay, so it means that I will color the tree using I will color the vertices of the tree using 3 colors. In my case, I use green, red, and orange. Okay, and I color a vertex Z in green if and only if it belongs to no maximal independent set. Okay, similarly, I color it in red if it belongs to all the maximal independent sets, and finally in orange in all the other cases. So if it belongs to some maximal independent set, but not all. Okay, let me give you an example. Here I have a tree with 5 vertices. Okay, we see that in this particular case, we have exactly 2 maximal independent sets. We have 1, 5, 3 and 1, 5, 4. So for instance, the vertex number 2 is in no maximal independent set, so I color it in green. 1 and 5 are in both maximal independent sets, so in red. And 3 and 4 are orange because they belong to only 1 maximal independent set. Okay, fine. So why do we care about this tricoloration? Well, actually, it turns out we have a really simple formula. If I call NG, NR, and NO the number of green, red, and orange vertices in a tree, I have this really simple formula that says that the independence number is the number of red vertices plus the number of orange vertices divided by 2. Okay, so it means that if you want to construct a maximal independent set, you can take all the red vertices and take half of the orange vertices. Okay, notice that it works only for trees. Okay, in general graphs, everything fails. But in trees, we have this nice formula. Also, let me mention that we have also another quite interesting relation. We have that the adjacency matrix of T, okay, so the matrix where you put zeros and ones depending on what vertices are linked. Okay, the dimension of the kernel of this matrix turns out to be equal to the number of red vertices minus the number of green vertices. Okay, so we have those nice formulas. So we won't care about the kernel dimension, but it was just to mention this formula as well. Okay, let me give you an example. Here I have a Bernheim-Galton-Watson tree with 100 vertices. Okay, and the offspring distribution is a Poisson distribution of parameter 1. Okay, and here I colored the vertices using an algorithm due to Chapoton. And to be, quickly, this algorithm does the following. You start by coloring all the vertices in one single color, red. Okay, you color everyone in red. And then you take a vertex, let's say, a vertex at random. Actually, it doesn't matter, but let's say you take a vertex uniformly at random, and you will apply to it some local rule, depending on the color of the adjacent vertices. Okay, you apply some rule, and you potentially change the color of the vertex you chose, depending on those local rules. Okay, and you do that a lot of times, up until the time where everything is stable, meaning that no matter what vertex you choose, the local rules won't change the color of your vertex. So when you obtain a stable tricoloration, let's say, you have indeed the tricoloration as I defined it previously. Okay. So let me give you some known results. So the first one is in the case of an offspring distribution following a Poisson distribution of parameter 1. Okay, this is what the P of 1 means. It means Poisson distribution of parameter 1. So this is exactly the same setup as the drawing here. Okay, this is the same setup. And in this case, we have some rather explicit formulas for the expectation of red, orange, and green vertices. Okay, so why does it work in this particular case? Well, actually, Tn with a Poisson distribution turns out to have the same law as a uniform KLA tree with n vertices. And in this case, you have some nice properties. Namely, if you reroute your tree Tn, you don't change the law. Okay, you are stable by rerouting the tree. And so you can obtain some nice induction formulas and so you can rather explicitly compute those quantities. Okay, but of course, this doesn't work if we are not in the Poisson 1 case. Okay, so now let me give you another result, which is more general. But this time, this is an asymptotic result. Okay, so first, I need to introduce a quantity, Q, which is the solution, the unique solution of Q is equal to G of 1 minus Q. Okay, where G is the generating function of mu. Okay, notice that Q always exists and is always unique. Okay. And the result is the following. So here, the hypothesis is way more general. We just need to suppose that we are in the critical case. Okay, so mu has mean 1. And we have some asymptotics for the expectation of the variance of the independence number. Okay, and we can see that the expectation of alpha of Tn divided by n is converges towards this constant Q. Okay, so this theorem implies a strong notion of convergence for the independence number. If we use this simple little lemma, so basically this lemma says that if you have a bounded sequence of random variables, if you have the convergence of the first and second moments, you actually have a convergence in LP spaces. So actually, this theorem gives us a convergence in LP spaces. Okay. So this is nice, but it's here we forgot the red, orange, and green vertices. So this is more general than the previous theorem, but we forgot the vertices, the red, orange, and green vertices. So our goal would be to find a similar result, a similar convergence, but for the number of green, orange, and red vertices. So we would like a convergence in LP spaces for those quantities. And this is exactly what we did. So it turns out that, so in the same setup, in the critical case, we have the convergence in all LP spaces of the number of red, orange, and green vertices divided by n, okay, towards some constants. Okay, notice that those constants are real constants, okay, they are not random. And those constants, you can see that the Q appears, and we also have G prime of 1 minus Q that makes its appearance. Okay. And of course, with that, we can retrieve the previous convergence in the consequence. Okay. But this is not strong enough to retrieve, for instance, the convergence of the variance. Okay. So actually, the theorem says a bit more for alpha of Tn because we capture the variance. Okay. For the time remaining, I would like to give you the idea of the proof. Okay, so for the proof, I will only focus on red vertices because, as you can guess, for orange and green vertices, it will be basically the same thing. Okay, so I will only focus on red vertices. Okay, and if you remember the simple lemma, okay, let me go back. The lemma says that if you show convergence of the first and second moment, you have what you want. So I will show the convergence of the first moment. Okay, the convergence of the second moment uses basically the same arguments, but it's just more technically complicated. Okay, but this is the same principle. So I will just focus on the first moment. Okay, and the key thing to do is to take the vertex Vn uniformly at random in my tree Tn. And I do it independently from Tn. Okay, so I draw Tn randomly, then independently I draw Vn among the vertices of Tn. Okay, and you just need to notice that the expectation of the proportion of red vertices is just the probability that Vn is red. Okay, so we need to find the asymptotic of this probability. Okay, to find the asymptotic, I will use the notion of local convergence. Okay, so I quickly recall what it is. So a couple tau u, where tau is a tree and u the vertex of tau, is simply a pointed tree. Okay, fine. And I define a notion of ball for a pointed tree. If I take an integer h, TUH is all the vertices at graph distance at most h of u. Okay, so you can see this as a ball for the graph distance. Okay, and I say that a sequence of pointed trees, tau n u n, converges locally towards tau u if for every ball, okay, at some point for n large enough, the balls coincide. Okay, so it means that if you look locally around un, at some point, it looks like what you can see around u in tau. Okay, so this convergence defines the topology called the local topology. Okay. Okay, so I recall that we are interested in computing the probability that Vn is red in Tn. Okay, and I will use this result that says that actually Tn Vn converges for this local topology towards some infinite random pointed tree, so star u0. Okay, so consequently, we have that the probability of Vn being red in Tn is converges towards the probability that u0 is red in T star. Okay, so we just need to compute this probability. Okay, before computing this probability, I want to tackle two questions. The first one is that, so T star has infinitely many vertices, okay, because Tn has n vertices, so if n goes to infinity, you expect T star to have infinitely many vertices. And remember that the tricoloration use the fact that the graph has infinitely many vertices, because the definition works if you have only infinitely many vertices. So what does it mean to be read in T star? Well, actually, you can generalize this tricoloration to some infinite trees, including T star. So luckily, T star almost surely belongs to the class of trees where you can generalize the tricoloration, such that all the good properties are still satisfied. Okay. Now I'm vague on what is a good property, but later I will explain what I typically call a good property. Okay. And the second question is that intuitively we want to say that being red or being green or being orange is more a global property of the tree. Okay, you need to know all the structure of the tree, but actually it turns out once again that we are lucky because in T star it turns out that being red for U0 is only a local property. So it means that almost surely you have a finite ball where if you know what happens in the finite ball, you know the color of U0 no matter of what's happening outside. Okay, so remember we want to compute the probability of U0 being red in T star. Okay, so I have no choice. I need to explain what is T star U0. So here we go. So we start with a chain of, well, a spine of vertices, U0, U1, and so on. And each UI, except U0, will have some children according to the law mu hat. Okay, and mu hat of K is K mu K. Can recall that mu as mean 1, so mu K is indeed a distribution, a probability distribution. Okay, and each UI minus 1 is identified as one of UI's children. Okay, so U0 is identified as a child of U1, U1 a child of U2, and so on. Okay, we are not done yet. Here we have a tree, but this is not yet T star. Okay, in our current tree, we have some leaves, including U0. Okay, here U0 is a leaf. And to each leaf of the current tree, I attach an independent copy of a Bellin-Galton-Watson tree with the law mu. Okay, so this is what I represent with those little bulbs. Okay, it means that I have attached a Bellin-Galton-Watson tree, an unconditioned, okay, a normal Bellin-Galton-Watson tree. Okay, and this is our final product. Okay, this is T star. This is T star. Okay, fine. And remember, I talked about some good properties of the tricoloration. So here we go. What is what I typically call a good property? So if I take K root T trees, T1, Tk, and if I denote by T1 star Tk, the tree obtained by merging the roots towards a new root. Okay, so I think the drawing is quite explicit. Okay, I merge all the roots towards a new vertex. Okay, if I do that, well, I have the good property, the following good property, which says that the root of T1 star Tk, okay, is red if and only if all the roots of T1 Tk are non-red. Okay. Okay, so if we keep that in mind, we can, for instance, compute the probability of the root of a Bellin-Galton-Watson tree being red. Okay, if I take an unconditioned Bellin-Galton-Watson tree and I take Q the probability of the root being red, I have a simple formula. Q is so the number of children, so the probability of having K children, which is mu K, and then the probability that each children is non-red, so 1 minus Q. Okay, and we retrieve Q is equal to G of 1 minus Q. So actually, this is where this Q comes from. It is the probability of being red for the root. Okay, this is where it comes from. Okay, and now I would like to do the same thing for another random tree, which I call T tilde, which I obtained by doing the following. So let me go back, maybe, yeah. So you take T star and you cut the edge between U0 and U1, and you get rid of U0 and its little bulb under. Okay, so you keep only what's happening for above U0. Okay, if you do that, you have T tilde. And you ask the same question, what is the probability of U1 being read in T tilde? So we use the same good property. Q tilde is just the probability of having k children, which is mu hat of k. And remember that mu hat of k is k mu k. Okay. Among those k children, you have k minus 1 children that reproduces like a regular Bellin-Hamilton tree, so 1 minus q power k minus 1. And you have exactly one child, which is not like the others, it's U2. Okay, and this one is non-read with probability 1 minus q tilde. Because actually what's happened, if you cut the edge between U1 and U2, and you get rid of U1, you have an infinite tree which has the same law as T tilde. Okay, so you have this nice formula. And finally, to conclude, the probability of U0 being read, so for the third time we use the good property. Okay, the probability of having k children for U0, which is mu k. Okay, those k children needs to be non-read. And you also have U1, okay, which reproduces like T tilde. And this one needs to be non-read as well. But this is not 1 minus q, but 1 minus q tilde. Okay, and if we put everything together, we exactly obtain what we wanted, which is q over 1 plus g prime 1 minus q. So, I think yes. So okay, so that's all for me. Thank you for your attention.
Thank you very much, Etienne. Are there questions?
Check on. Yeah, check.
Yes.
Oh.
I have another question. Thanks for the talk. I was thinking between many, so the result you obtain is really on the infinity. And we know that a lot of graph class, like sparse graph, converge the probability towards 3.
Yeah.
So can we figure it out? We don't have, I think for graph, we don't have this nice connection between the number of green and red vertices.
But
Number, but can you say something like bounds or?
So what works for this case is that actually you need some okay, so maybe for the first moment maybe it will work, but for the second moment actually we need to prove that when you take two vertices at random uniformly in your tree or your graph, you need to be locally independent. And so if you, I don't know if it's possible to have a family of random graph where this fails, but still we have a local convergence towards them. Yeah, so, but yeah, maybe.
No questions online. Any questions online?
Okay.
So is there a question now from earlier? Oh, this is from earlier. I think so. Oh, you're right. Wow. So there's one that says possibly one question in the article. We had some Gaussian limit results, but not in full generality. We had some non-zero variable condition, which we did not succeed to prove, but for all the types of trees and offspring, we have some progress.
Yeah, so I see what it means. No, actually, No, not really, to be honest.
For next year.
Yeah.
For next day.
Exactly.
So, thank you again.
Okay.